Alrighty. So, today we are beginning chapter 17, which is now our third chapter on equilibrium. Uh, it's just stuff we never stop doing, it seems, in 113, which is alright, because we're going to see that this is all the same concept just applied to more and more situations. So we're going to talk about all sorts of things now, kind of bridging up beyond acid-base chemistry. We're going to talk about solubility. We're going to talk about formation of complexes, rather. We will, of course, be talking about acid-base chemistry, but we're going to see that there's a bunch of other stuff that we're going to do with this equilibrium concept still. So, with that, the first thing we're going to introduce, I mean, there's really kind of no distinction between distinguishing these as different chapters because it's all equilibrium, it's all using ice tables, it's all the same idea. So it's just kind of adding more and more things to the examples. So the first section of this is the common ion effect, which I can't spell. And this is essentially just Le Chatelier's principle in context. So it's basically saying, if you mix two solutions that have a common ion between them, you can mess up the equilibrium. It's just a way of messing. We talked about how certain equilibria, you can push them right or left, depending on adding or removing products, right? So this is essentially the same idea here. So we're going to say that maybe we can mix a solution of HF and is calcium fluoride soluble? Probably not. So maybe how about we do magnesium fluoride? Let's assume that's soluble. We're going to see that this solution would have these two ions floating around in it. And this solution would have these two ions floating around in it. And we're going to see that this is going to mess with our equilibrium if we were to mix these two solutions. Because they both have the fluoride ion as part of them. So by mixing these solutions with a common ion, we disrupt the equilibrium. So let's go ahead and do this. So let's say we are going to be mixing a solution of, I don't know, 0.1 molar HF and a solution of magnesium fluoride are mixed. And we're going to say that let's do equal volumes of each. Okay. Let's just have a couple more bits of this. If we have the pKa of HF, which I swear we've used so many times by now, I should have it memorized, but I don't. Let's see, HF is 3.14. Okay. And then we're going to assume that the what's called the solubility product constant for magnesium fluoride is much greater than 1, so we're going to just assume that it just acts as a completely strong electrolyte, where we're not going to have to worry about its effect on the equilibrium. So let's just go ahead and assume that. So basically what we're doing here is, therefore, since we're going to ignore the equilibrium of magnesium fluoride, we're really looking at this one here. We're looking at this equilibrium, but now we have some fluoride ion in there. So if we go ahead and take this into consideration, so we're mixing solutions of HF and magnesium fluoride. If they're going to be mixing in equal volumes, we're going to have half of each one, right? We're basically doubling the volume for each solution by mixing them together. So that should mean our concentration should be divided by 2. Hopefully that part makes sense, right? M1V1, M2V2. So we know we're starting with 0.05 molar hydrofluoric acid, and we're starting with 0.075 molar of the fluoride ion, and we have no H plus ion in there, assuming there's no acids around. So, of course, if we look at Q right now, remember that's hydrogen times fluoride over HF. It equals 0. So Q is definitely less than K. Ka, I guess, in this case. So we know that the reaction will proceed towards the products. So we know that we're going to be consuming HF. We're going to be producing the other two. And so if we go ahead and set our Ka expression up, we have X times, this value, and that was 10 to the negative 3.14. So we can solve the X here. If we wanted, we could try an assumption, and we would end up with X being, let's see, what is that going to be? 1.5x equals that 10 to the whatever. We could see, we can try that, but let's go ahead and just solve for X mathematically here. So let's pop it into Wolfram and see what we get. All right, so our equation is X times 0.075 plus X divided by 0.05, minus X equals 10 to the negative 3.14. Okay. Let's see what we get here. Hopefully I've typed everything in properly. Okay, we get a value here. X is 0.000475,353. We also had a negative value in there that would not make sense because it's bigger than the other one. Okay, so with the assumption, it's pretty close either way. So, and what's the percentage on that? Probably, let's see, that should be less than 5%, yeah, because that's 2 orders of magnitude, so it's about 1% or something, a little bit less than 1%, so we should be okay. So we're good. That would be molar there, and so we can see that if we go ahead and look at these, our HF concentration will be 0.05 minus this. With proper sig figs, are we even going to have a difference? Very slightly, we will have a difference here with sig figs. 0.05 minus all this crap. Let's let's just put that in there. If we do that, we get 0.0495. Guess I could have done that in my head. Molar with sig figs. With our H plus, we know that that's going to be just the value that we get for X. And then the F minus, we're going to have... Oh, wait, we messed this up, didn't we? The MGF2 should have had twice as much. Here, you know what? We'll change this. We'll make this problem easier. There. Problem solved. Whoops. So we should have done double the concentration of F minus because there's two F minus. Creature shush. There's two F minuses for the magnesium one, but we'll just pretend that we didn't see that. So let's go ahead and do the other one. 475, which will equal 0.0755 molar with proper sig figs. So this would be our kind of answer here. So really the only difference for... Actually, I guess what ions, right? So we don't even care about HF, but whatever, we did it anyway. So that would be our answer there. So we do end up decreasing our HF concentration just a little bit. So we do end up producing a little bit more fluoride. Sometimes we'll end up producing a little bit less. Interestingly enough, we can see this in another context in just a second. But first, any questions on this one? Or if you use the assumption, I mean, whatever the numbers you get, they should be the same. The only thing, your H plus will be 0.000483 instead. It's just fine. Your other numbers will not be changed, though, with sig figs, so we'll be okay. Alrighty. So if there are no questions, then let's do another example. So let's say we had a mixture of HCl and acetic acid. See, those two are mixed. And so let's say that our solution is here. We'll make it easy this time. We'll make the numbers work out nicely. Again, we'll do equal volumes mixed here. So our common ion this time is, what's it going to be? Our common ion here is H plus, right? Yeah. So we know that HCl has a Ka that is much, much, much greater than 1. So we can kind of ignore that one again. But we know that this guy definitely does not have a Ka of that. We can look its Ka up. It's going to be like 1.6 times something. 1.76 times 10 to the negative 5. Yeah. All right. So we know that the equilibrium we're messing with here is our acetic acid equilibrium. So that's the one we're going to be using for our ice table. So if we're going to mix equal volumes again, that means our concentrations should be halved. Here, let's throw another in there. Again, Q will be equal to 0, so of course we're going to be subtracting X. If we do this again, we have our equilibrium concentrations here. So we get X equals, what was it, 1.76 times 10 to the negative 5. That's our Ka. Let's do our assumption here. So x will be equal to 1.76 times 10 to the negative 4. I can do this in my head, yes. Yeah. Oh, no, yeah. Okay, cool. So with the assumption we get that, and that is definitely less than 1% of 1. So, or less than 5% of 1, so we're okay there. So with that in mind, we can use this assumption. And so if we go ahead and look, we're going to see that our acetic acid concentration with sig figs is unchanged. Still 1 with our sig figs. The H plus concentration is unchanged with sig figs. But we do have a, what is this? I don't know what that is. Okay. We do end up, however, with a small concentration of acetate. So, we see, interestingly enough, that all the H plus in this solution, it all comes from HCl. Oops, not the acetic acid. Interestingly enough, and I mean, perhaps we expected this because HCl is strong, right? So, it's kind of expected that way. So, normally you would expect some coming out here, but overall, because the H plus from the hydrogen chloride was so much bigger, we overall have completely nullified this equilibrium. And so we can see that overall, almost no acetic acid will dissociate. I.e., the equilibrium is disrupted. So we're going to see that this common ion idea can be used to force an equilibrium to go one way or another. So nothing necessarily new there. It's just a kind of looking at Le Chatelier's principle in more context. So, normally we would expect, okay, yes, this, acetic acid should be producing some H plus, but by throwing in a bunch of H plus, we're forcing the equilibrium to really go back the other way so that we don't actually break apart our acetic acid at all. All right? Any questions on that? All right, then. We'll move on to our next section then, where we can talk about buffers. Or more accurately, buffered solutions. We'll start with our kind of definition here. A buffer is a mixture of a weak acid plus its conjugate base. I guess I should write it that way. So it's a mixture of a weak acid and a conjugate base. So if we take a look at that, we can see in the context of a common ion how this is going to work. So when we have a weak acid and a conjugate base together, we're going to see that this, several things can happen with the solution. So if we add an acid to this buffered solution, we're going to see that the new H plus that we're putting in will react with our conjugate base, and it will neutralize it. And conversely, if we add a base, we're going to see that the new hydroxide formed, or equivalent base thereof, would react with the weak acid, which will completely neutralize that added base. So what we can see here is that buffers resist pH change overall. Because if we add an acid up to a certain point, we're going to be able to react all of that acid away. And if we add a base, we're going to be able to react all of that away as well, up to a certain point. That point, by the way, is called the buffer capacity. Is how much this can resist. And I think I have a video of this. Let's go ahead and let's see. Let me pop up my textbook here. And let me just go ahead and check. I'll be able to show you what it looks like when we throw a buffer solution, when we start trying to change the pH of a buffer solution. Alrighty, so let's go ahead and show the screen here. Let's go ahead, go to acid-base stuff. Buffers. Okay, so here is an example where I have a solution of just a universal indicator that's just going to change colors when we adjust its pH. And so to these solutions, I'm going to be adding either hydrochloric acid or sodium hydroxide. And we're going to be able to see what's happening here. Okay, so here's our first 1 drop of acid there. Change it to yellow. If we put 2 drops of acid, we kind of get this orangey color. And then you see a whole bunch of acid, perhaps. Yes, lots of acid. We're going to get a nice, yeah, they'll go crazy. We get red color. So the indicators are just showing us a relative pH range. And so we're going to see that that red color is strongly acidic. And now if we mess with bases, we'll end up getting these darker colors. And you can see just a few drops is enough to change their pH such that these colors are changing. And so we end up with this lovely rainbow of various pHs. Exciting. So, however, this was just in water. So we just had solutions of water. We're adding 1 drop of HCl, 2 drops of HCl, 3 drops of HCl or whatever, and then same with the base. If we look at it with a buffer now, so here, same solution, but now it's buffered. So we have, I think, some acetic acid and sodium acetate in here. We're going to do the same thing. Let's zoom ahead here. Okay. Add a drop. Add 2 drops. 3 drops, I guess. Add a whole ton of acid. Stir them up. Aha, no pH change this time. Let's just be sure. Let's try with the base side. Add a couple drops of base. Add a lot of base. Stir those up. Again, no change. So all the extra acid that we add will be able to react with acetate. and with the base, it'll be able to react with acetic acid. I don't remember if I just do a ton of it as well in one of these. Yeah, throw in the whole thing of it. And we see a very slight change of pH. Maybe. It's still green, right? So we can see that we can really mess with buffers in this sort of context. Okay, cool. It's always nice to see kind of in context there. In this class, however, we would probably use a pH meter instead, because for that class it's equivalent of 101 here, so it's baby chemistry. So we just use colorful things. So we're going to see that if we take let's say we have a solution of, you can do that acetic acid and sodium acetate. So let's say a solution has half molar acetic acid and half molar sodium acetate. Oops. We saw last time that this would have a pH roughly equal to the pKa of the acid, which is going to be true. Let's say that we add... Let's add 10 ml of 1 molar HCl to this solution. Let's say we're going to add... let's add it to 90 mils of this solution. Let's see what happens here. So, if we have more, this time we're not having equal volumes. So, if we have this 0.05 molar, and we're going to be multiplying it by 90 over 100, that means we're going to have 0.450. And for our 1 molar HCl, we're going to really be having 0.1 molar of that. So with the volumes that we've put in here. So again, just using the M1V1, M2V2 idea. So the molarity and the volume. So we had 90 mils originally, but now we're at 100 mils. So we have diluted both of these solutions. So we can see here that if we put our equilibrium up, this is really what we're starting with here. Oops. Oh my goodness. So let's go ahead and see what happens. For this, we don't even actually know right away, do we? We would actually have to evaluate Q. So, because we don't know which way this equilibrium is going to shift, although we are adding an acid to it, so we would expect it to go left. But let's go ahead and see. Let's see what Q is going to be. So Q is 0.1. We saw that Ka for this, or Kc, let's say Ka, was 1.76 times 10 to the negative 5. Yeah. So we see that Q is actually greater than Ka. So we are going to shift to the reactants, right? We're going to make more reactants. And this made sense, right? We're throwing in an acid, so we should expect to react with the base. So, oh my goodness, we have no room. Oh no. Maybe we can make this work. Can we move this slightly out of the way? Here. Here, we'll just throw this down here. Our work for Q. Okay. So Q again tells us the direction the reaction will go. So, with that in mind, this is actually an easier one to solve, right? Let me actually move this over a little bit further. Let's move it over there. Yeah, good enough. Our Ka is going to be equal to 0.1 minus x, 0.450 minus x, 0.450 plus x. If we make our assumption, we get that 0.100 equals to 1.76 times 10 to the negative, whatever it's going to be, 5. So that assumption will not work, right? We can't just say that that's going to work. So assumption is invalid. So we're going to actually have to calculate it. So we bust open our Wolfram alpha. Let's go ahead and do this. So 1.76 times 10 to the negative 5 equals 0.1 minus x times 0.45 minus x divided by 0.45 plus x. Doing all this stuff, you need to go away to shift to reactants. Let's go ahead and solve for x here. We get x equals two options, one of which is not valid. So we're looking at 0.09999. It's going to be what we're looking at here. Or if we round that, x is 0.1. Notice that our H plus concentration is 0.1 minus x. Oops. So, what does this mean? It means that all the added H plus from the HCl is used up. And therefore it cannot affect the pH. Or it's going to be a very minor change in the pH. So we kind of made the assumption there that our the acid from the acetic acid was negligible, which I mean, technically we did an earlier exercise where we saw that the acid from acetic acid is negligible compared to the acid from HCl. So this HCl that we've added doesn't really affect the pH. Technically, we have reduced our acetate and increased our acetic acid a bit, but overall our H plus doesn't really change. So we've used up all this extra H plus. So, lucky us, we don't have to worry about that. Our H plus is going to be roughly the same as it was before. And so we will have not changed our pH, even though we added, a not negligible amount of a strong acid. We didn't change the pH. All right, so we can see here how buffers are going to be working. And it's going to be the same if we added a base instead. We would just be reacting away some of the acetic acid instead of the acetate. So our equilibrium will go the other way. So we would use Kb instead for that. So with that in mind, we can take a look at the Ka for a buffer system. And we're going to see that we can actually figure out the pH of a buffer solution a little bit more easily than having to deal with these pesky ice tables. So we know that Ka is going to be H plus times A minus over HA. Nothing new here. If we take the log of both sides, or let's say the negative log of both sides, so remember, if we multiply two things together, remember log of x times y, because log x plus log y, we're going to see that we get this relationship. Just by having this go together. If we go ahead and substitute these, and we say pKa equals pH minus log A minus plus log HA, and do some rearrangement, if we solve this equation for pH, move everything to the other side, and just move some stuff around. Let's kind of recombine that as a logarithm. Remember, subtracting logs, therefore, is the same as dividing them. If we do this, we can figure out the pH of a buffer solution by just looking at this directly. This is called the Henderson Hasselbalch equation. You, of course, will not need to learn to spell that. But let's go ahead and evaluate this. So let's go ahead and take now our pKa's, or rather our information from the last problem we did. And let's see what the pH is going to be after we added that HCl and before we added the HCl. So the pKa for acetic acid, where did it go, is 4.75. So let's see before we added the HCl. I don't need to do that. Okay, before we added the HCl, we had equal concentrations of each one, right? Nothing changed there. Remember that the log of 1 is 0. So the pH for that original equation was 4.75. pH equals pKa when we had the equal amounts of each one. So let's see what happens to the pH after we add the HCl. If we have the same equation, oops. Again, we're going to have 4.75. But let's go ahead and look now at our actual equilibrium concentrations. For our acetate ion, our A minus, we ended up subtracting 0.1, so we have 0.35 then of acetate, and we have 0.55 of the acetic acid. So 0.35, 0.55. If we do this, We're going to have to, of course, use Google or a calculator. Log 0.35 divided by 0.55 plus 4.75 equals 4.55. So we do end up becoming a little bit more acidic after adding that HCl, just a little bit though. The HCl by itself was what, 1 molar, I think? Or whatever, 0.1 molar. The pH for that would be 1, right? Or if it was 1 molar, I forget what it is, the pH would be 0. Regardless, the HCl's pH would be much, much lower, right? And so we saw that our solution before had a pH of 4.75. We're mixing it with a solution that either had a pH of 0 or 1. I don't remember. I could easily scroll up, but doesn't matter. But we end up with a solution that has a pH of 4.55. Much, much closer to our original buffer pH than this acid that we've added. So, again, the point here, buffers resist pH change. That's the whole idea here. Is so even chucking in a whole bunch of a strong acid, we didn't really change our pH. It's very close to what it used to be. And this is a pretty severe amount of acid that we've added to this. So we've thrown in quite a bit of acid, but still it didn't really change our pH. And so that we're going to see that biological systems, buffers are going to be super, super important. Extremely important for biology. In fact, our blood pH is just about 7.4. If we go, let's say, if we end up having a blood pH of 7.3, we are in acidosis. If we are at 7.5, we are in alkalosis, and we die. Our blood pH must stay 7.4, otherwise we will die. Very bad things happen when your pH goes awry. The chemical reactions that need to take place within our bodies are very, very sensitive to pH, because these enzymes that control all of the reactions that are happening in our bodies will change their shape if they're at different pHs. And if they change their shape, they don't work anymore. And so without the catalyst to make things work, the reactions don't take place. And if the reactions don't take place, you die. So, all this stuff about, drinking alkaline water to kill cancer or whatever is kind of BS, because your body is very, very pH sensitive. And it has numerous mechanisms, including 3 specific buffer systems, to prevent your body's pH from changing. So you have very, very tight regulation going on there. So, try as you might, if you try and change your blood pH, you will die. So yeah, it'll kill your cancer cells, but it will also kill you. So perhaps it's not the best treatment. So just keep that in mind. So the blood, for example, has the bicarbonate buffer. Has significant concentrations of bicarbonate in there. Also of various phosphates. And then proteins also work as buffers. So you have these 3 kind of buffer systems in place that very tightly hold blood pH at 7.4. All three of these. So if you try adding bases or acids to your blood, the bicarbonate, the various phosphates, and the proteins will all act to counteract that addition. So you have actually a pretty good buffer capacity in your blood that it's very tightly controlled here. So interestingly enough, your lungs and kidneys really take care of this, mostly through that bicarbonate. The bicarbonate is really the major one in your blood. And we're going to see that your blood is controlled by the lungs by breathing out carbon dioxide, and then by your kidneys by either absorbing bicarbonate back in from your urine, or pre-urine, I suppose. So these two organs are very good at controlling this. They can control the amount of bicarbonate in your blood by looking at by controlling how much CO2 you breathe out, as well as how much bicarbonate your kidneys reabsorb from the pre-urine. So if you try and hyperventilate by losing CO2, by understanding that this is the equilibrium here, by making the carbonic acid, if you try and breathe out your CO2, you will go into alkalosis and pass out, at which point your lungs and kidneys will reassert themselves and they'll fix the problem before you die. But that's why you'll pass out, because your body's like, what are you doing? Stop hyperventilating. Not a good thing. So that's why if you are hyperventilating, you'll breathe into a paper bag so that the CO2 you breathe out, you'll breathe back in and not mess up your blood pH. Not mess up those buffer systems. However, if you do pass out, your lungs will take control again, and your kidneys will also reabsorb more bicarbonate. So everything here is very tightly controlled. That's the whole point here. And if you try holding your breath, not breathing out your CO2, you'll go into acidosis, and the same thing will happen. You'll pass out, and then your lungs will start breathing out that CO2, and your kidneys will stop reabsorbing bicarbonate, and things will go back to normal, and then you'll regain consciousness, and blah, blah, blah. So, yeah, our bodies are very, very good at maintaining this pH. And so you have buffers in various areas. One area we don't really have a buffer is the stomach. We like to make that quite acidic because we have enzymes that work very well in acidic conditions that are designed to work that way. And these acids also help to break down other proteins that you're digesting. So there are certain areas of your body where you're not going to have buffers, and there are certain that you will. Your urine is also buffered by various phosphates and bicarbonate, but not to as great of an extent as your blood or cells are kept. So buffers are super, super important. If you end up doing any biochemistry research later on, you're going to see that like half your time is going to be spent making buffer solutions to conduct your experiments in, where you'll be very tightly maintaining your pH for your cell-based experiments or protein-based experiments or whatever, simply because the buffers will keep things where they need to be. So, am I off my pedestal now? Perhaps. That's kind of it with buffers. So, we're going to look at tomorrow. We have 10 minutes. I don't want to start the next kind of topic yet. So, tomorrow we're going to look at titrations. We're going to look at acid-base titrations. We're going to look at strong acids, strong bases, weak acids, strong bases, weak acids, weak bases, all sorts of various mixtures, how these are going to work experimentally. We're also going to look at titrations with buffers involved. So we're going to see kind of graphically that we're going to see that pH not changing over the entire length of the buffer capacity. For your homework this week, since we're just starting the chapter, your homework will probably not be due this Sunday. Oh, excuse me. All depends on how far we go, but probably it'll be due next week. Um, as a result, I have made 2 simulations that will be due this weekend. So you'll have one on advanced acid-base chemistry, which is going to deal with more weak acids and stuff, calculating pHs and using pH meters and that sort of thing. And you'll also have a titration there, so you'll be able to kind of assemble your acid-base apparatus, so you can see how it's going to work. So that's going to be your focus for this weekend. I will be putting up your homework probably tomorrow or Wednesday, but that'll be due next week. Our exam is in 2 weeks. It will be on the acid-base chapter, this chapter, and the next chapter, which is environmental chemistry. Again, most of this stuff is all going to be equilibrium, so don't forget your equilibrium concepts from chapter 15. It's all going to be important here. Equilibrium expressions, Q, using your ice tables, all that sort of thing is going to be super important for your exam, so don't forget that stuff. All right, so I guess I should also try and find some more practice exams for you guys, so you can work on this sort of thing. So I'll go ahead and do that as well. Awesome. So with that, I guess we're good to go. So I'll see you tomorrow. We'll talk about our titrations. We'll go on from there. And yeah, so with that, see you tomorrow. Have a great Monday. Enjoy the rest of your day.